Hi everyone, welcome to the start of a new series. We are looking now at trigonometry once again. Now, we talked about trigonometry in last year's content, and I introduced the SOHCAHTOA and finding all these different angle values, side values of right angle triangles. Now, what I want to do in this series, at least at the start of it now, is to run you through just a bit of an investigation. It'll be a little bit more drawn out than usual, but this is an investigation into how we can make sense of the idea of a trig ratio in the first place. And what I'm going to be using in order to teach this is this massive table that I've got here. Now, if you went to school any time in the last 10 to 20 years, you've probably never seen something like this because, like me, you would have had the luxury of just using a calculator where we didn't even need to look at essentially what was happening here. We could just do trig as we need to. But hopefully by the end of this video, I'm going to be using this table in order to give you an idea for how SOHCAHTOA, what we introduced in the last series, actually works and why the values it comes out with essentially make sense. Now, what I have here is a trig table which would have been used prior to calculators being invented and used across the board in schools. And what these trig tables gave us were a column with the different angle values. So this goes all the way from angle 1 to an angle size of 90 down the bottom here. And it also had the different trig ratios here. Now, we're still going with this idea of my sine being the ratio or the fraction of the opposite side to the angle over the hypotenuse, my cos being adjacent over the hypotenuse, and my tan being the opposite over the adjacent. Now, what I want to do is first of all look at a couple of extreme cases here. So these really small angles here. So for example, with an angle degree of 1 and 2. You may notice that, well, the sine values, these are really, really small. And the cos values are very, very close to 1. Now we want to have a look at why that actually is. And this will hopefully give us a bit more intuition as to how these ratios essentially work, and hopefully give us a bit more of an appreciation for what people would have had to go through using these tables way back in the day. We're going to be using these tables to solve some problems later on in the series, but we're just investigating a couple of things in this video, and maybe in the next one if it becomes a two-parter. So I'm going to look at these extreme values of, for example, an angle of 1 and 2. I'll also look at a couple maybe here of an angle size of 86 and 87. So what I've drawn down the bottom here is what a triangle would roughly look like if we had a really small angle. Now, a tiny angle means that these two angle arms, this one and this one, they're going to be very, very close together. So as we draw our angle out, the side opposite to that angle is going to be pretty small relative to the other ones. Now, my adjacent side, because that adjacent side stretches out with my hypotenuse, so it's going to be pretty long as well. Now, the opposite here is a little bit different. This is quite small relative to my other sides. So I've made a couple of notes here, and this is going to be some observations that we are going to make here. So say we looked at sine here, the ratio of the opposite side over the hypotenuse. Now, the opposite side here is pretty small. So when we set up a fraction or a ratio for sine, I'm going to have a pretty small number as the numerator and a bigger number as the denominator. So when I divide a small number by a big number, let's just think of what we might expect to get as a fraction or a decimal. So a small number, say 1, getting divided by a bigger number, maybe 20. If we pop this into our calculators, we're going to get 0.05. We're going to get a small number. We're going to get a decimal, in fact. And if we have a look up on our table, so taking this idea, we're going to expect a small value for my sine at the angle of 1. And lo and behold, that's what I end up getting. Because when we do trigonometry, when we introduce SOHCAHTOA, it's all about understanding ratios and fractions and how these two sides interact. Looking at cos now, I have an adjacent side that's pretty big relative to the opposite, and I have the hypotenuse, which is the longer side. That's the side opposite to my right angle. So I'm going to get, for cos, a bigger side / a bigger number, and my hypotenuse is going to be also a bigger number, but it's going to be ever so slightly bigger than my adjacent. So if we think of this as a fraction, this is a bigger number, let's say for example 19, over a slightly bigger number on the denominator. Now I'm just pulling these numbers out of nowhere. These are just little thought experiments to get you thinking about how these sides interact. So if I have a bigger number divided by a slightly bigger number than that, I'm going to get something quite close to 1, aren't I? If I do, for example, 19 over 20 in my calculator, I'm going to get 0.95, a number that's pretty close to 1. Now, in this case, for a very small angle of 1 degree, the size of the adjacent is going to be almost the same as the hypotenuse. So we're going to expect to get a fraction, when we convert it to a decimal, as something really, really close to 1. And as we see, our cos, that is going to be a number quite close to 1. It's still not a whole number, and it will never be a whole number, because so long as the hypotenuse is on the bottom, where it is for sine and cos, the denominator is always going to be bigger than the numerator. So if we look at our table here, you can actually see if we traced through and looked at all of the sine and cos, we never get a number bigger than 1, do we? I've always got these. We have a couple of special cases here. We'll talk about those later, way down the line. But all of these values, they're fractions, well, decimals when we convert them, that are less than 1. Why? Because the hypotenuse is always the biggest side. The denominator here is always the biggest number. So we will never get more than a whole. Okay, let's look at one more example. Let's look at tan here, and we'll look at tan maybe of, just to change this up, of 2 degrees. It's going to be quite similar, but investigating tan here, we have a smaller side, O, because remember our tan links our opposite to our adjacent. So we have an opposite side, which is pretty small, over a adjacent side, which is quite big. So once again, we're going to expect a small fraction, or in a small decimal, when we convert this across. Now I've written this here. My tan theta links my opposite over my adjacent. So we have a pretty small number over a bigger side relative to the opposite. So when we compare these, we would expect a pretty small decimal. And as we do for all of these smaller angles, we're always getting these quite small decimals. Because trigonometry at this stage, it's all about understanding the ratios, and these change for different angle sizes. So let's take another example where we look at a bigger angle here. For example, 86 or 87. So in order to draw a big triangle, well, a triangle with a big angle, I have something really close to 90 degrees. And let's look at how, if I have this as my angle, my other two sides have to compensate. So my opposite side gets way bigger now, and my adjacent side gets really tiny relative to that. So the angle actually changes how my right angle triangle looks. So going down here, if I drew this with a bigger angle, you can see my sides, especially my opposite and my adjacent, they compensate. The opposite has now gotten bigger than in the previous example. The adjacent has gotten smaller. So the trig ratios are going to change. Now let's look at sine. That links the opposite with the hypotenuse. So now in this case, when the theta, the angle theta, is bigger, I have a ratio of a pretty big side over a slightly bigger side here. I've written that here. I'm looking at a fraction, because sine theta gives me a fraction of a pretty big opposite over a slightly bigger hypotenuse. Let's think of what this would give me. Well, once again, it's not going to be greater than 1 because the denominator is bigger. It's the biggest side here, the longest side. So I'm going to get a fraction pretty close to 1 though, because the opposite is still very close in size to the hypotenuse. So if we scroll back up to our table, look at that. Our sines are quite big. Even as I go to the 80s and the 70s, they're still numbers really close to 1 because that's what the ratio is. The fraction on the right hand side gives me a big number over a slightly bigger one. So it's going to be a decimal very close to 1. Now, conversely, looking at the opposite here, sorry, the adjacent, looking now at cos, which links my adjacent to my hypotenuse. Putting this as a fraction gives me a pretty small side, because the adjacent here is small relative to the other sides of my right angle triangle. It has to be smaller to compensate for this bigger angle. So I'm going to get a pretty small numerator over the longest length denominator, because the hypotenuse is the denominator here. Now, if I did this as a fraction, I would expect quite a small fraction, because I'm dividing something small by something big. So I will likely get something small. Let's see if it trends as we expected. Look at this now. We have some really small values when we look at cos up here. As my angle gets bigger, my cosine ratio gets smaller. Look at all these decimals. They're closer to 0 than they are to 1. They're really, really small. So these sides and how their ratios and how they relate, they change based on the angle length. They interact in different ways. Now let's look at one more example here of a tan ratio. Now tan relates the opposite to the adjacent. Now opposite is on the numerator. Now this is a quite a long side relative to the adjacent. So we're going to have, if I express this as a fraction, opposite over adjacent, I have something big divided by something small. So that's what I've written here. I have my opposite's big, my adjacent is pretty small. So if I had this, I'm dividing a number by a smaller number. So let's just think about that. I'm dividing a something on the top by a number that's smaller than it. I'm going to get a number bigger than 1, aren't I? Anytime I take a number bigger and divide it by a smaller number, I'm going to get a number greater than 1. This gives me 4. This gives me 9. This gives me 2. So I would expect my tan ratio when the angle theta is pretty big to be something greater than 1. And here there's quite a large discrepancy. My opposite, as the angle gets really, really big, my opposite's going to be way bigger than my adjacent. So I would expect my tan here to be quite large, and in fact larger than 1. Let's look if that behaves as we predicted. It does. Look on this right hand side. My tan ratio, that relates my opposite to my adjacent. My opposite's big relative to my adjacent. So dividing opposite by adjacent, it gives me numbers when the angle theta gets quite big, numbers bigger than 1. So this is the essence of what we're doing when we solve these trigonometry questions. We are looking at how sides relate. And as angles change, how do the sides compensate? Let's just do one quick thought experiment, little example down the bottom here. If I, for example, drew a triangle with a really, like I've done before, a really massive angle here. So my theta is pretty big. If I draw this triangle, my opposite, I can't even draw these angle markings because the adjacent is just so small relative to my opposite. But now, as I change this up, so let's take a slightly smaller angle here. Looking at this angle now, this is somewhere in the middle, and my opposite and my adjacent, these are now starting to change a little bit. Now they're closer in length. Now as the angle gets smaller, my opposite and my adjacent change. They get, well, one gets smaller, the opposite gets smaller, the adjacent gets larger. These side lengths are compensating now in order to preserve this actually being a triangle. So we can keep doing this. As I make the angle even smaller, my opposite gets smaller, my adjacent gets bigger. And ultimately, let's give ourselves a bit more room. If I made the angle really tiny, this like minuscule little angle, my sides will adjust. I'm going to get a small opposite, my angle is here, and my adjacent is going to be longer relative to my opposite. Now the hypotenuse is kind of chilling here, to be honest. The hypotenuse is always the longest side. It doesn't really mind what happens. It just always connects to opposite adjacent, and it always just sits as the longest side, opposite to the right angle here. Hypotenuse isn't as interesting, but there's this constant give and take thing happening between the opposite and the adjacent. And we can see this here. As I progress through from left to right, I can see this in action. I can see how these opposites and adjacents change relative to one another. Here, my opposite is big. My adjacent is small. Here, my opposite gets smaller, but it's still kind of a bit bigger. So the ratio is going to be different. And as I go here, for example, my opposite is once again, keeps getting smaller. And as my opposite gets smaller, my adjacent gets bigger. And finally, my opposite is at its smallest, my adjacent is at its biggest. Now, I'm not talking about big in terms of like length here. It's the length relative to the other. It's the interplay between the opposite and the adjacent. Here, the adjacent is really big relative to how small the opposite is. Here, my opposite is really big relative to how small the adjacent is. But we'll talk a little bit more about this in future videos when we look at similar triangles and how these ratios may or may not change as we make, for example, even bigger triangles, right angle triangles. But more on that in the next video. This hopefully will give you a little bit of an intuition as to how the trig ratios change and why we have so much variety when we look at this table. You can even take your calculator, substitute in some values of theta, some different angle values, and see what your calculator spits out. And you will see a variety of different values here. It looks a little bit scary, but it's also quite intuitive how it works. But that brings us to the end of the video. Thank you so much for joining me, and I'll see you next time.